Okay, welcome back. We're going to continue talking about binary search trees. And here in part B of this lecture, I really have just two objectives. The first is, as I said in part A, I'd like you to get to learn basically the rotation operations that are fundamental tools to balancing binary search trees. Basically interchanging nodes a little bit. They're really low-level operations, and how you can use them in a strategy at a higher level to actually balance the binary search tree. That's something that we won't get involved with. We'll just settle for learning the basic rotation operations. Yeah, and the other thing I'd like you to do as you study more binary search trees in part B, I want you to really take seriously the code, as I've asked you to do in the past. I want you to download and study either the C++ or the Java version of the binary search tree code that I've supplied. Okay? By now you should have done a fair amount of this kind of thing, checking code, getting it to run, really trying to understand what it does, maybe experimenting with it, altering it, and so forth. I want you to do that sort of thing with my binary search tree code as well. All right, so let's get into these rotation operations. There are two of them. One is called rotate left, and the other one is called rotate right. The names maybe are not exactly perfect because, well, depends. I mean, they're about as good a names as any, I suppose. Maybe rotate clockwise, rotate counterclockwise might be better. But anyway, let's look at what these operations are about. And really, this is a case of picture, worth 1,000 words. So let me save my breath and just show you this stuff in action. Well, better talk a little bit here. So let's imagine that a node X has a left child node Y. Okay, in that case, it's possible to do a rotate right operation on this pair, at the end of which X will become the parent, X will become the child of Y. Okay, we start off with Y being a child of X, but after the rotation, it's the reverse. Okay? We start with Y being a child of X, a left child of X, and when we're done, we'll have X becoming a right child of Y. So let's visualize the initial situation. Simple enough. Okay? Y is the left child of X. X might or might not have a right child, and Y might or might not have a left child and might or might not have a right child. Okay, here's what the transformation does. Okay, Y goes to the top and X becomes its right child. All right, so that looks pretty simple. And of course, the rules make sense. In the initial setup, X was the left child of Y, so X should come... in the initial setup, Y was the left child of X, so Y should come before X in the ordering. And here, X is the right child of Y, so again, that means that Y should actually come before X in the ordering. All right, it looks simple, but there's more to it, because we do have to concern ourselves with these other pointers a little bit. Okay? The main technical issue, a subtlety. There's a subtlety here, and you cannot exactly detect it from the figures that I drew. So pay attention to this subtlety and actually go back and look at the figures and see if it doesn't make sense to you. Okay, here it is. It's possible that in the original setup, Y might have had a right child already. Well, that would present a problem now because we're going to rearrange things so that x become y's right child. Okay, so we have to do something with the original right child of y. Okay, so here is the deal. It's actually quite simple, but easily overlooked. If y originally had a right child, then you got to change things so that that node becomes the left child of x. What used to be the right child of y must now become the left child of x. Okay? And that's it. That's really the only subtlety in this rotation. Okay? Because now if y had a left child to begin with, well, good news, that's unaffected. Okay? That left child can continue to be y's left child. And similarly, if x had a right child to begin with, then we want to leave that alone. We want to end up with that still being x's right child. Okay? Here's another detail that you might probably expect. If x is not the root node, then of course x must have a parent to begin with. In the original configuration, if x is not the root, then x would have a parent, right? And we need to change things because y is going to become the parent of x. So here's what we have to do. The original parent of x must now become the new parent of y. And that makes sense because it used to be that x was above y, and when we finish, y is going to be above x. So whoever used to be above x will now become above y. That's basically all that's saying. Okay. So the move that we just did was called a rotate right, and you probably guessed that if you understand rotate right, you understand rotate left. It's a symmetrical thing. Okay, we just have to basically do the same thing in the mirror. Okay. So I won't bother to talk about that further, draw the pictures, but I think you could go draw the figures for yourself, be very clear how a rotate right works, and then you should be able to figure out rotate left by doing the same thing in the mirror. Okay, so we're going to try to use these rotations to take a particular unbalanced tree and balance it, just to get a feel for how this goes. Okay, I think I will just look at the pictures and talk it out briefly with you. So take a second and remember the highly unbalanced binary search tree that we had at the end of the Part A notes. Okay, you recall pretty much looked like a linked list. The node with value 2 was the root. Its right child was the node with value 3, and its right child one with value 5, and so forth and so on. Okay, so starting at the top there with the nodes whose values are 2 and 3, originally 3 was the right child of 2. And we can do this simple rotation right here, and you can see what happens, right? 3 gets elevated and becomes the parent of 2. Yeah? 3 is now the root, and 2 has become its left child. Okay? 5 continues to be the right child of 3. All right, that's a good start. We're obviously improved the situation a little bit, so let's continue. So we'll do another rotate left, and this time we did it with the pair 3 and 5. Okay, we had 5 being the right child of 3, but now 3 has become the left child of 5. And pretty much everything else is the same as before. 5 has become the root, so of course we have taken the pains here to reset the root pointer in the binary search tree object to reflect that. Okay, this next rotation I did using the pair 6 and 8. If you need to, flip back to the previous slide to see how it was, but I don't think you need to. We had 5 followed by 6, followed by 8, followed by 9, all going off to the right. Yeah? So we had 8 being the right child of 6, and then after the rotation, they've sort of switched levels, and 6 is the left child of 8. 9 continues to be the right child of 8. Okay? And now it's basically balanced. All right? Now, this was a very small, simple example, and admittedly, it did not show off the subtlety that I mentioned where you sometimes have to intervene a little bit more to, yeah, well, you just have to change things a little bit more in some subtle cases. Anyway, we're not going to make too big a deal of these rotations, so let's just continue.